Hello viewers, welcome to Big Boy Physics. Today is the first day to start with the problem of fluid mechanics and properties of matter. I've taken this problem from a famous test series. Well, I guess you can guess it from the font, the text, all those, from which institute I have taken it. Okay, so let's get started. The question says that as shown in the figure, a long, tall, cylindrical body of density rho is equals to 3 gram per centimeter cube, and radius is small r is equals to 5 centimeter, and length h is equals to 20 centimeter, moves along the axis of a vertical, tall, cylindrical vessel of radius capital R is equals to 10 centimeters, filled with liquid of density rho naught. Assume that there are no energy losses anywhere. Rho naught is equals to 1 gram per centimeter cube. The vessel is closed from top to top and bottom. First question. It says that what will be the acceleration of the cylindrical body, and second is the what will be the pressure difference between the upper and the lower bases. Well, in this video I'll be solving only question number 3. Question number 4 I'll say you the answer at the end, and you will take it as a homework. I'll try to say. Try question number 4 by yourself. Question number 3 will give you a lot hint about question number 4. Okay, so pause the video, give few minutes, and try this question. Okay, so let's get started. If you are a student and you have used v is equals to rho gh, sorry, v is equals to what I'm writing, b buoyant force, bf, that is buoyant force, or fb is equals to v rho g, where rho is the density of the water, that will be rho naught, and answer will come out to be rho minus rho naught g by rho. By this method you'll get some answer like this. Well, apparently you are doing in the wrong direction. This is a wrong method. Why? Because I'll explain. Now, in cases where you use v is equals to rho gh, what is the condition? That the vessel in that case is too large. The vessel is too large that if there is a body and its volume is negligible to the sea or the vessel, then what will happen that it will just go down, and there will be basically negligible effect due to the fluid. Now in this case, the body has size comparable to the tank. What will happen in this case basically is, when the body will go downwards, then there will be three regions created. First region will be the vertical region, which is contained by the side walls of the cylinder and the tube, which is given as region 2. The upper region is given as region 1, and the lower region, most region, is given as region 3. When the body will try to accelerate, region 3 will remain at the rest. Now, what about region 2? Region 2 will accelerate. Why? I will explain. Well, you can see region 2 will accelerate because of equation of continuity, all those concepts, right? Because when the body has gone down by some region, some distance x, then what will happen to this amount of water? This will basically flow outwards, right? That is why region 2 will have some kind of definite acceleration, whereas region 1 will also be at rest. Okay, so when region 2 will accelerate, basically the pressure difference, what we write V rho g, is due to the pressure difference. In this case, the pressure difference will change. That is why the acceleration will be uh, rho, the acceleration will be somewhat different. In this case, there will be some different g effective when we write P difference is equals to rho gh. In this case, this g will not be exactly that g which is equal to 10 meter per second square, but rather it will be some g dash. Okay, there will be some other factor. Hope you get it. Now to find the acceleration of second portion, I can use Newton's laws of motion, basically some dynamics and Bernoulli's concept, equation of continuity, all those. Well, another method is I will be showing you is work energy method. Going with Bernoulli's theorem, I am observing this motion in frame of the body. Basically, what will happen is that in frame of the body, I am sitting on the body, and it accelerated downwards with A. Since with respect to lab frame, 3 is at rest, that is why with respect to body, 3 will go upwards with acceleration A. Now region 2 will also have acceleration, but it will not be A, it will be rather A dash. So A dash times pi capital R square minus small r square is equal to A times pi times capital R square, which I have written is equation of continuity. So A dash will come out to be A times of capital R square by capital R square minus small r square. Okay. Now what will be the acceleration of region 2 in lab frame? Well, the body is going downwards by A. So just put minus by A both in the A dash expression minus A. You will get the acceleration of region 2 is equals to A times of small r square by capital R square minus small r square. And if you try to evaluate, it will come out to be A by third. If you put the value R is equals to all those, it's given R is equals to 10 centimeters, small r equal to 5 centimeter. If you put all these values, you will get A by third as the acceleration of region 2. Now, if you remember one, you may have done a problem that here's a vessel and here's some water. Suppose the vessel is accelerating in a frame upwards, then we say that pressure difference between the topmost portion and the bottommost portion, the P diff, that is the pressure difference, is given as rho g into A plus H. Now, in this case, also the region 2 is basically accelerating upwards. So, pressure difference between the flat surface, that is P diff, is equals to A by third plus G into rho G, where rho is the it will be sorry, it will be rather rho naught. Rho naught is the density of the fluid, and if you multiply with pi r square, small pi r square, it will give the net downward force on the block due to the pressure difference. Okay. Hope you get it. Right. Sorry, it will be upward force rather, because here the pressure will be excess and here the pressure will be lesser. So it will basically give me the net upward force, right? And we know that the net downward force will due to the gravitational attraction, which will be rho times pi small r square into g into h minus rho naught g pi r square A by third plus G into H. Here will be another G, which is equal to rho times pi r square G, no sorry, A times H, cancelling pi r square H, and putting rho, just we need to keep rho as it is, because basically it will be cancelled due to the ratio. So you'll get G minus rho naught by rho. What is rho naught by rho? It will be 1 by third into, here won't be any G, into A by third plus G is equals to A. So basically you will get 2G by third is equals to A by 9 plus A, which is equal to 10A by 9. Hence you will get acceleration to be 6G by 10, which will come out to be 6 meter per second square. And that's the answer. So the answer to the first part, that is the acceleration of the cylindrical body, will be 6. If you do this method that is I am showing, which is rho minus rho naught g by rho, you will get 3 minus 1 by 3 into 10, which will nearly come out to be 6.67, I guess. And that's the wrong answer. Well, when I asked few of my friends about this question also, they also talked about the answer 6.67, but rather the answer is 6 meter per second square. Yes, it's all due to the fluid flowing across the cylinder, that is between the body's walls and the tube. Okay, so this is the method using basically all the stuffs of dynamics and Bernoulli's theorem, equation of continuity. Then second method, coming to second method is work energy theorem. Okay, as derived in previous step, that is acceleration is given as a r square a dash minus a, that is of the region 2, is given as a r square minus small r square. If velocity of body is small v, then what will be the velocity of region 2? it will be v small r square by r square minus r square, which will come out to be v by third. Using conservation of energy, you will get 1 by 2 pi r square h rho into v square plus half pi capital R square minus small r square into h, that is into rho naught. This is the mass of the second region. Okay, since it's flowing between the tube and the walls of the cylinder, so this is the mass of the second region into v square. V2 square, which is equal to v square r to the power 4 upon r square minus small r square whole square. And observe one thing here, there's a key point to observe. Suppose initially my level is somewhere here and my cylinder is here. Now it has gone or descended by some distance x. Observe one thing, that the cylinder's gravitational potential energy has decreased, whereas if you had considered water present here, it has apparently shifted to this position. So basically there will be shift in the mass. Okay, you will get minus pi r square h into rho minus rho naught into gx. Now differentiating with respect to time, you will get, and cancelling on the pi r square h term, obviously this is very messy, this pi r square h term, you will get, end up with rho v dv by dt plus rho naught v dv by dt into small r square plus capital R square minus small r square, and then you will get is equals to rho minus rho naught g. What is dx by dt? Dx by dt is v. Now cancel all the v, you will get dv by dt. What is rho? Rho is basically given in the question to be 3. 3 plus 1 into 1 by third is equals to 3 minus 1 by third into g. You will get, you will end up with something like 1 minute. So basically my final answer will come out to be dv by dt is equals to g times rho minus rho naught by rho plus small r square by capital R square minus small r square into rho naught. You will end up with 3 plus 1 by third, 3 minus 1 into 10, and the final answer will come out to be 6 meter per second square. Hope you understood this problem. And second part is your homework, which is asking my pressure difference between the upper and the lower bases. Well, I am providing with the providing you the answer to the second part. Well, the answer to the second part is 2400 in pascals. It hope you easily crack the second part, because I have almost given all the hints. So thank you and have a nice day.